The LHC, a 27-kilometre tunnel 100 metres below ground, accelerating protons to unprecedented energies along a ring of magnets and radio frequency cavities so we can learn more about the fabric of the universe. If you're one of the long-time viewers of this series, you're probably familiar with this one-of-a-kind setting for our videos. But the LHC is such an intricate engineering marvel that there's always more to learn about this machine. Small details, little things like, for instance, did you know that there are 2 rings in the LHC tunnel, not just 1? If you don't believe me, let's take a peek from above the magnets. For most of the tunnel, the second ring is kind of hidden behind the ring of iconic blue magnets. But in specific spots like this one, it stands out above them. In today's video, we're going to shine the spotlight on this unsung hero, the small ring, without which the larger, more famous ring would not function. This is the second part in our adventures at low temperatures. Before you watch this video, make sure you've seen part 1. In it, we saw how the dipole magnets are very like advanced vacuum flasks, with a design which drastically reduces the energy transfer from the tunnel to the superconducting coils. But we also said that we can't completely block that energy transfer. There's still always a small amount of heat threatening to sneak into the coils. In this video, we're going to focus on how the second ring prevents that from happening. At its core, it relies on the physical phenomenon of phase transitions. So today, we're going to look at what phase transitions are, when they take place, how we use them for heating or cooling, and whether we can use just any phase transition for heating or cooling. Let's begin. Liquid water boiling and turning into steam is an example of what we call a phase transition. Water is transforming from one state of matter into another, here from a liquid to a gas. In the last video, we introduced thermal energy and separation energy. The more heat an object absorbs, the higher its temperature and the weaker the attraction forces between its molecules. So, once a certain amount of heat is absorbed, the kinetic energy of the molecules is going to be higher than the potential energy holding the material together. The molecules will stop working together and start acting more independently. The material transforms into a looser, more disordered state of matter. At standard atmospheric pressure, this corresponds to water having absorbed enough energy to reach a temperature of 100 degrees Celsius. The opposite change, back towards the liquid state, happens if enough heat has been extracted from the steam to transition towards a more united phase, corresponding to the steam being cooled down to 100 degrees Celsius. So a phase transition is the process through which a material changes from one phase to another as a consequence of a transfer of energy. You've probably heard about states of matter before, so today we'll focus on the less familiar aspects of this field of physics. But just so we're on the same page, let's quickly go over the basics. It's often said that there are 3 states of matter: solid, liquid, and gas. You may also know that most ordinary matter in the universe is in a 4th state of matter: plasma. Creating a plasma requires separating electrons from nuclei instead of simply rearranging molecules in space. So it's a bit different from the usual trio. We won't be covering plasmas today. Something you may not know is the difference between a state of matter and a phase. Some materials can have different phases within the same state of matter. You know diamond from wedding rings and graphite from pencils? Well, they are 2 phases of the same material, carbon, in the same state of matter, the solid state. It's just that the carbon atoms are arranged differently in each phase at the microscopic scale. And that translates to a huge difference in terms of appearance and price at the macroscopic scale. Some materials even have multiple liquid phases, but that's a topic for another video. On a slightly different note, you probably also know the names of the various transitions between those states of matter. Let's go through them all really quickly. Ready? Changing from a solid to a liquid is melting. Changing the other way from a liquid to a solid is freezing. Okay, that was easy. It gets trickier now, so let's focus. A liquid turning into a gas is vaporization. Yes, you heard that right. The other way, a gas turns into a liquid by condensation. And last but not least, a solid can turn into a gas directly, skipping the liquid phase entirely by sublimation. And the other way, a gas becomes a solid by deposition. Okay, I think we've got them all. Bingo! Okay, I might have got a little bit overexcited there. Let's collect our thoughts and look at what we have in this diagram. Freezing and melting are easy. We know them well from everyday life, with ice. Condensation is also a familiar phase transition. We see that happen often when water vapour in the atmosphere forms little droplets on cold surfaces, like the mirror in your bathroom after a shower, or the windscreen of a car in winter, or a chilled aluminium can in summer. Sublimation and deposition are a little more tricky. At standard atmospheric pressure, carbon dioxide, or CO2, can only exist in two states of matter. Above minus 80 degrees Celsius, it's a gas. Below minus 80 degrees Celsius, it's a solid. This is a chunk of solid CO2 made at minus 80 degrees Celsius, now warming up at room temperature. It is so cold that water vapour in the air deposits on top of the carbon dioxide and condenses on the glass around it, so it forms little snowflakes and little water droplets. Meanwhile, the CO2 turns from a solid into a gas. You can't see CO2 gas, but you can see the solid CO2 shrinking and disappearing until eventually everything is gone. The leftover liquid is water from the air. There was never any liquid CO2 in this experiment. In daily life, deposition is responsible for all the annoying buildup of ice in your freezer. It seems like it appears from nowhere, but really it's just the water vapour from the air which has turned into ice on the cold walls of the freezer, without ever being liquid water in the process. Okay, so there's one phase transition left, vaporization. And for this one we need to spend a little bit of time setting some things straight. If you thought this was called boiling, or maybe evaporation, you're not alone, and you may not be wrong. Here's the deal, boiling and evaporation are two types of vaporization. Evaporation is vaporization happening at the surface of a liquid, while boiling is vaporization happening throughout the volume of the liquid. At the microscopic scale, not all molecules or atoms move around at the same speed. Let's imagine we find extremely fast molecules at the surface of a liquid. Maybe they have so much kinetic energy that they have overcome the attractive forces that hold the rest of the liquid together, so they escape. These molecules form a gas phase above the liquid, also known as a vapour, which is usually invisible. The process is known as evaporation. In the vapour, though, the same thing is happening in reverse. Slower molecules in the gas that are moving towards the liquid can get caught by the attractive forces at the surface and condense back to the liquid phase. So the liquid and the gas states keep exchanging molecules. Okay, so time to blow your mind. This is not liquid water. This is liquid water and water vapour. As soon as you have a material in a liquid state, in a container that's bigger than the volume of your liquid, you also have the same material in a gaseous state above it. In fact, each liquid likes to hang out with a specific concentration of its own molecules in vapour form. Cooking oil is happy with very few of its molecules in vapour form. Water needs a few more. Rubbing alcohol wants a lot of its molecules to be in gas form. If the concentration of vapour molecules in the air is too low compared to what the liquid likes, then more of the liquid will evaporate to make up for it. That's why at room temperature, rubbing alcohol evaporates quickly, water evaporates slowly, and cooking oil barely evaporates at all. Okay, we just watched water evaporate. You must be thinking it really can't get any more exciting. But we can turn up the heat even more. Time to start talking about boiling. Boiling is when vaporization happens not only at the surface, but also in the volume of a liquid. Pockets of vapour inside a liquid are called bubbles, so it makes sense that we see bubbles rising up in boiling water. Now, a bubble can only appear if the gas it's made of is able to push back on the liquid around it. So we need the pressure exerted by the gas to be at least equal to the pressure exerted by the liquid. But that pressure is mostly determined by the air pushing on the surface of the liquid. So boiling can only happen if the pressure of the vapour is greater than atmospheric pressure. There are two ways to ensure that this is the case. First, we can increase the pressure of the vapour. And we can do that easily by increasing the temperature. That's the type of boiling we're used to. At higher temperatures, molecules have, on average, a higher kinetic energy. So any molecules escaping the liquid to form a gas phase will be faster and they'll push harder on their surroundings. Second, we can decrease the atmospheric pressure. And we can do that easily by decreasing the concentration of air molecules. This is warm water in a syringe sealed off with a bit of tape. When we pull on the piston, we decrease the pressure and the water boils. That's a second, lesser known way of boiling. Of course, the two are connected. If the air pressure is lower, then we don't need to increase the temperature as much to induce boiling. That's why the boiling point of water is lower at the top of a mountain. In the end, boiling is the form of vaporization that matters in the context of phase transitions. Boiling is a sudden change which happens when the liquid's temperature or the atmospheric pressure reaches a certain point. while evaporation is a slow, gradual change happening at any time. So in this chapter, we got familiar with phase transitions, which are the process through which a material changes from one phase to another as a consequence of a transfer of energy. And we spent some time telling the difference between evaporation, a phase transition that happens at the surface of a liquid at any time, and boiling, a phase transition that happens throughout the volume of a liquid when the conditions are just right. This bottle is just out of the freezer. It's full of liquid water and it's weirder than it looks. Its temperature is about -3 degrees Celsius. It looks like we caught this water in the act of breaking the laws of physics. Here come the physics police. Arrest that water! Hi, do you know why I pulled you over? Do you know what temperature you're at? -3 degrees. But at standard atmospheric pressure, water should be in a solid state below 0 degrees, shouldn't it? Okay, here's what we're going to do. We're going to drop an ice cube into your bottle. Ah, very good. I see you can be in the right state with a little help. And your temperature is back to 0 degrees. Seems like things are in order. All right, we're letting you off with a warning this time, but don't let us catch you at it again. Water freezing at 0 degrees Celsius at standard atmospheric pressure is a universally acknowledged truth about phase transitions. Yet, it does not necessarily mean what you think it means. It does not state that water will freeze at 0 degrees Celsius, only that it can freeze at 0 degrees Celsius. In the previous chapter, we talked about how phase transitions happen in response to an energy transfer. But in order to undergo a phase transition, all materials need a little bit of help. The energy transfer only enables the transition, it does not actually trigger it. The very first bubble, droplet, or crystal of the new phase needs something to attach to in order to grow. In most real-world situations, this is not a problem. Materials are full of imperfections, little scratches, specks of dust, and these can provide a nice space for the phase transition to begin. But if you work with materials that are extremely pure, the transition may never happen at all. A material is said to be in a metastable state if it has not changed state in spite of an energy transfer, which would normally cause a phase transition. In the first part of our experiment, the water is in a metastable state. It stays liquid, despite having been cooled down below 0 degrees Celsius, so it is in a supercooled state. For supercooling to happen, the bottle needs to be very clean and smooth, and the water needs to be very pure with very few dissolved minerals. At CERN, we can even use tap water for this experiment, as we get our water from Lake Geneva, which is naturally very pure. A metastable state is a bit like a house of cards. If you leave it alone, it is stable, but if you nudge it, even in the smallest way possible, it will collapse. That's what the word metastable means. It's stable, unless it's disturbed, in which case it's unstable and it transitions to another state. That's the second part of our experiment. An ice cube is a good place for more crystals to grow, and the whole liquid turns into a solid very quickly, which is the expected stable state of matter at 0 degrees Celsius. At this point, we've learned lots about phase transitions and under which conditions they actually happen. In the rest of the video, we'll investigate how phase transitions can be used for cooling or heating and how this links to the LHC. But we can't just leave metastable states behind without pointing out how helpful they've been in the field of particle physics. Today, we rely on giant digital instruments like CMS or ATLAS to detect elementary particles. They're a bit like extremely advanced digital cameras. Back in the day, though, experimental physicists had to operate analog instruments, a bit like old-fashioned film cameras. This is a cloud chamber, and this is a bubble chamber. They are big vats of fluid in a metastable state, which can detect elementary particles. Let's start with cloud chambers. They've been around since the early 20th century and rely on supersaturated vapour as a metastable state of matter. In the previous chapter, we said that liquids like to have a certain concentration of their molecules as a vapour above them. Well, under some conditions, you can get that vapour in a supersaturated state. This means two things. One, the vapour concentration in the air is too large compared to what the liquid would like. And two, these extra vapour molecules are stuck in the gas state. They can't find anything like a dust particle, which would help them condense back to the liquid state, because the air is very clean. And that's exactly why supersaturated vapour is a good particle detector. This is what a cloud chamber looks like in action. It is crisscrossed by a mesmerising pattern of ever-evolving condensation trails. Each trail tells us that an electrically charged particle has passed through the chamber. Here, most of the particles we detect come from the collision between high-energy particles travelling through the cosmos and the molecules in the Earth's atmosphere. When an electrically charged particle passes through the supersaturated vapour, it can knock an electron out of any gas molecule, creating an ion. This ion is the perfect imperfection the extra vapour molecules need to condense back to the liquid state. So the vapour molecules form a droplet around the ions that the particle creates. And so, as the particle moves through the chamber, it creates a train of droplets, the condensation trails. But cloud chambers are difficult to scale up. As scientists wanted to build bigger instruments to detect even more particles, they had to develop another type of detector in the middle of the 20th century, bubble chambers. These rely on superheated liquids as a metastable state of matter. That's a liquid that is heated up past its boiling temperature, but remains in the liquid state. Just like with cloud chambers, when an electrically charged particle passes through the chamber, it creates ions, which in turn help gas bubbles to form. So the signature of particles passing through the chamber is vaporization trails, like the ones on these photographs. At CERN, we still keep the structure of some of the biggest bubble chambers in the world on campus, like this one, or that one. There are tons of Nobel Prizes associated with each of these early particle detectors, for inventing them, for improving them, and for using them to make landmark discoveries. So despite having been replaced by more convenient digital technologies, metastable states definitely left their mark in the field of particle physics through their application in early particle detectors. They correspond to matter not changing state in spite of an energy transfer which would normally cause a phase transition. And they can collapse with very small disturbances. This is water being heated up at a constant rate. Below 100 degrees Celsius, the temperature rises steadily, but when we get to 100 degrees Celsius and the phase transition begins, the temperature gets stuck. It's not rising anymore, even though we're providing heat to the water at the same rate as before. The fact that the temperature stays constant while absorbing energy is very interesting, particularly if we have an engineering application in mind. Let's say, the cooling system of a giant particle collider. In the first video in this mini-series, we introduced the concept of specific heat capacity. We said that some materials don't increase their temperature as much as others when they absorb energy. But here we have a situation in which a material absorbs heat without increasing its temperature at all. That's infinitely better. So in this chapter, we have 3 things to figure out. Why doesn't that heat change the temperature at all? What happens to the heat during a phase transition? And can we harness this heat in some way? Let's go over what we know so far. We know that once an energy transfer ends, heat becomes internal energy. We know that heat can be stored in the form of thermal energy, increasing the temperature of the object, or in the form of separation energy, weakening the attractive forces that hold the object's molecules together. We also know that if enough separation energy is stored, and if there's a good starting point, a phase transition can begin. But now it makes sense that we would need more energy for the phase transition to move forward. Water vapour is not just liquid water with no attractive forces between its molecules. At the microscopic scale, the molecules are arranged in a very different way in each phase. We see many consequences of this at the macroscopic level. For instance, liquid water at 100 degrees Celsius is 1,500 times more dense than water vapour at 100 degrees Celsius. So, to get from a liquid to a gas, we need energy to rearrange the molecules of the material. We'll call this transformation energy in this video series. Transformation energy is a form of potential energy associated with the molecular reorganization happening during a phase transition. The only time it comes into play is during a phase transition, and it's the only component of internal energy available when the phase transition occurs. So now we know what heat becomes during a phase transition. It is in a very exclusive relationship with transformation energy. The fact that none of the heat becomes thermal energy is actually quite a peculiar behaviour. Physicists give a specific name to energy in transit that doesn't end up changing a material's temperature. They call it latent heat. Latent is an old-fashioned way of saying that something is inactive or hidden. The total amount of heat being exchanged over an entire phase transition from its beginning to its end is called the latent heat of transformation. Some phase transitions in some materials involve a very large latent heat of transformation. Consider a volume of liquid water at 99 degrees Celsius. It takes a certain amount of energy to heat it up to 100 degrees Celsius, but it takes 540 times more energy to heat it up to 100 degrees Celsius and transform it all into steam. In other words, the latent heat of vaporization of water is 540 times larger than the specific heat of water. That's a lot of energy. For vaporization, that's energy the material needs to absorb, but for condensation, the opposite transformation, that's energy being released by the material. Overall, a phase transition going towards a more disordered state absorbs energy from its environment and cools the environment down, whereas a phase transition going towards a more ordered state releases energy into its environment and warms it up. In other words, boiling a liquid cools the surrounding environment down, and freezing a liquid warms it up. Maybe this all sounds a bit abstract, or maybe you're not entirely convinced. It sounds really strange to say that boiling cools stuff down and that freezing heats stuff up. But the trick is to remember that stuff here is not the material undergoing the phase transition itself, but its surroundings. When you hang clothes to dry on a rack, the evaporation of the water from the clothes draws energy from the surrounding air, and so it cools down the room. In winter, snowflakes form through the condensation or deposition of water vapour, which releases energy into the air. So snowy days are slightly warmer than non-snowy days. We could go on, but actually we can do something better. Let's see latent heat. So far in this mini-series, we've watched water evaporate, boil, freeze and melt. Exciting stuff, right? Well, this time you're going to see something totally out of the ordinary. We're going to put a piece of paper on top of a glass of water. No, seriously though. This is a dish with water in it. As you know, there's also water vapour on top, as liquids never hang out alone. Through an infrared camera, it doesn't look like much at the moment, as everything is at room temperature. If we place a thin sheet of paper on top of the dish, the water vapour condenses under the paper, and the paper heats up. See this bright circle? It's a fraction of a degree hotter than everything else, just because the water vapour is condensing on the paper. Now, if we remove the dish of liquid water, the tiny droplets on the paper evaporate, and the paper cools down, so we see a dark circle. It's a simple experiment, but with pretty cool results. Another, less subtle situation, where we can visualise the latent heat of a phase transition, is with hand warmers, the kind people might use on a cold winter day. This pouch is filled with a solution of sodium acetate in water. If we bend the disc in the middle of the pouch, all the sodium acetate crystallises rapidly. We started with liquid sodium acetate in water, and now we have sodium acetate crystals in water. So a phase transition from liquid to solid just happened in the pouch. We can detect the latent heat being released by this phase transition in the infrared. It's warming up the surrounding water in the pouch and releasing a lot of latent heat, so it's really quite warm at the end. On a side note, the transition happened very fast and may have reminded you of the supercooled water we played with a bit earlier. That's because we started with a supersaturated solution in the pouch. That's another metastable state. All right. So by now, you should be convinced that a material undergoing a phase transition can absorb or release a lot of heat while keeping its temperature constant. Let's see how we put this fact to good use in the dipole magnets of the LHC. In the previous video, we took a look at the many layers in and around the cold mass with its superconducting coils, which we want to keep at a temperature of around 2 Kelvin. We focused on the outer layers, which shield the cold mass from almost all of the heat coming from the tunnel. Almost. There's always a little bit of heat left, sneaking past the outer layers and into the cold mass. That's where this pipe comes to the rescue. It's a heat sink. It rids the cold mass of the residual heat. Each heatsink is a 107-metre long copper pipe which goes through the cold masses of several magnets like beads on a string. Inside the tube flows a small stream of helium in a liquid state with a lot of helium vapour on top. The helium is at a temperature of 1.8 Kelvin and the cold mass is at 1.9 Kelvin, so this small temperature difference sets up an energy transfer from the cold mass to the helium. The pressure in the tube has been adjusted so that the helium is ready to undergo a phase transition at that temperature. So the liquid helium absorbs the heat without increasing its temperature by turning into helium gas. Every 107 metres, each heat sink is connected to the smaller ring hidden next to the main ring of the LHC through one of these protruding sections of the machine. This is where the smaller ring performs two jobs. It gets rid of the helium gas coming out of the heatsink, and it tops up the liquid helium going into the heatsink. Basically, it ensures that there's always enough liquid and not too much gas in the heatsink, so that any extra energy can be absorbed by the latent heat of vaporization of liquid helium. Alright, and with that we have a fuller picture of how the LHC is kept so cool, by being encased in a high-tech vacuum flask and by vaporizing liquid helium. So in this chapter, we've learned that the molecular reorganization happening during a phase transition either requires or releases heat, known as latent heat of transformation, and that this occurs at a constant temperature. We can harness that latent heat for cooling or heating. But we've actually got one last thing to cover in this video. It turns out that some phase transitions don't even have a latent heat. We'll finish this video with a whole new state of matter and a whole new class of phase transitions, and we'll introduce them with this very tiny vial. It's full of carbon dioxide. Some of it is a gas and some of it is a liquid. Now you might be surprised to see CO2 in a liquid state, and you'd be right to be surprised. That's only possible because it's been sealed inside the vial under pressure, at almost 73 times the atmospheric pressure. Under such a high pressure, liquid CO2 does exist at room temperature, and the CO2 gas becomes very dense and compressed. In these conditions, carbon dioxide has a phase transition at 31 degrees Celsius. Let's use an infrared lamp to heat it up to trigger this phase transition. Focus on the lines separating the liquid from the gas. It's getting thicker and fuzzier. And it's gone. That was both beautiful and baffling. Well, our carbon dioxide did not go through an ordinary phase transition. Something quite unique just happened. As we heated the CO2, more of the liquid evaporated, building up the pressure into the vapour phase and making the gas denser and denser. At the same time, the liquid expanded more and became more and more agitated. At 73 times the atmospheric pressure, when we reached the temperature of 31 degrees Celsius, the densities of CO2 gas and liquid CO2 become equal. This is known as the critical point of carbon dioxide. The distinction between liquid and gas disappears and both phases turn into one single state of matter, a supercritical fluid. Supercritical fluids have some properties of gases and some of liquids, but they're their own state of matter, only found at relatively high temperatures and pressures. In the LHC dipole magnets, the fluid which flows through this pipe is actually helium in a supercritical state. It cools down the thermal shield we discussed in the previous video, keeping the shield at a temperature of 80 Kelvin. It flows like a liquid, but being much less dense, it has a lot more swirls and eddies, which is good for carrying heat away through convection. The phase transition to a supercritical fluid is a very subtle, subdued one. The transition is a gradual, continuous change of the properties of the two phases until at some point they just become the same. Because the phases involved in the transition are so similar, there's no transformation energy required for the material to switch between states. Now compare this to boiling, for instance. There's none of the drama. There's no latent heat being absorbed, there's no vigorous bubbling. Just for the beauty of it, let's see what happens when we cool a supercritical fluid back into a liquid and gas. We saw a flash of a cloud, and then the familiar line dividing liquid and gas reappeared. Actually, that wasn't a cloud. That was the supercritical fluid starting to turn back into a liquid and into a gas everywhere all at once. The phase transition back from a supercritical fluid is also gradual and continuous. The properties of the supercritical fluid become more and more dissimilar until at some point, some regions become a liquid and some become a gas. So this little vial just broadened our horizons a lot. We've just learned that there are two types of phase transitions. On the one hand, there are the phase transitions we know and love, which we've been studying in all the previous chapters of this video. They are called discontinuous phase transitions, and they're very common in our daily lives, like boiling. During a discontinuous phase transition, there is a latent heat of transformation involved, and pockets of the new phase appear abruptly and coexist with the old phase for a while. On the other hand, there's a whole new class of phase transitions, like the one we just saw with supercritical CO2, which are called continuous phase transitions. During a continuous phase transition, the properties of the material change smoothly and no latent heat is involved. Continuous phase transitions pop up in more specialised contexts. And would you believe it? That includes the engineering of the LHC. In the next 2 videos of this series, we'll see many examples of continuous transitions happening in the materials that give the LHC its superpowers. Stay tuned for 2 more videos, one about superfluids and another about superconductors. Thanks for learning with us, and see you soon.